Key ideas in quantitative finance, the elimination of randomness. We want to transform the problem of pricing derivatives from stochastic to deterministic. How can we do it? Well, this question is fundamental because we have a problem that is described in terms of stochastic variables. Take the stock price. Stock price is something that changes all the time, and looking at the stock price as a process, it has to be regarded as a stochastic process, a random process that changes and it goes up and down all the time. Indeed, there are many mathematical models that describe how the underlying behaves in financial derivatives, and these are all stochastic differential equations describing then this process as being all the time jumping, going up and down, perhaps with certain tendency. But here we're doing black magic. We're doing black magic because on the one hand, we have this random process, all jumpy, with many breaks, discontinuous, and this could apply to stocks, for example, or to any other asset class that we can have in mind. And what we want to do is transform that stochastic, that random problem, in something deterministic. So take away the randomness. Indeed, what we want to do is to eliminate the randomness. How can we do that? Well, it's possible to do it. And first, we have to start with the stochastic part, with the random part. We start with the process that describes the underlying, let's say equity, which is geometric by motion, in which we have the classical stochastic differential equation that describes the changes in the price of the equity as a function of time. So we have all these trajectories that we are used to when we look at the evolution of the stock price in time. So we're in the stochastic world now. What we're going to do now is we're going to apply Ito's lemma to this process of the stock price, such that we find what is the result of the change in the price of the stock in terms of how it affects a function of this price. This we have represented here in terms of function f, which depends on capital S, which is the stock price, and little t, which represents time. So what we want to do is to have some representation that will tell us, if we know the behavior of the underlying, what will be the impact on a function of that underlying. And that function of that underlying is going to be the price of the derivative, because as we know, the derivative is a contract that represents a price that depends on something else, on the underlying. And therefore, we want to see if the underlying moves in a certain way, how the price of a derivative contract that depends on that underlying behaves. So what we are going to do is to construct a portfolio. This is going to be composed of a financial derivative, which is F here, and a number of stocks, which is the underlying, which is delta. We're going to look at what happens with the variation, so with the change in the value of this portfolio between one moment and the other. And of course, that will depend on both, on the price of the underlying and the price of the derivative. And on delta. Delta is a scalar, is a constant that we're going to control, and that is going to allow us to eliminate the randomness. But for the time being, it's just a constant. So we can put these things together, and we can look at the change in price of our portfolio, capital I, and by substituting the formulas together, we obtain a representation of what is the change in the price of the portfolio in terms of variations of the option price with respect to time, as in the first term in the in the equation on the bottom of this page, of the first derivative of the function of the option in terms of the stock price, in terms of the convexity or gamma, that is the second derivative of the option, and in terms of also the Wiener process that we used before to model this random movement of the underlying. And here is where the magic is going to happen. In this formula, we're going to choose that the number of stocks that we hold is going to be equal to the partial derivative of the price of the option with respect to the underlying. That is partial f with respect to s. If we do this, then we're going to cancel a lot of the terms that we had in our previous equation, and we are going to end up with this, what we call this formula below, that represents the change in value of the portfolio between one moment and the other, where we don't have anymore this stochastic term. This, in fact, has allowed us to go from stochastic to deterministic. And this formula is very important because with this formula, we can go to the deterministic world. And in the deterministic world, we can do the classical things that we do in corporate finance, in which we look at the change in price of the portfolio. That is going to be the initial price, considering the interest rates and the amount of time, the delta t that we have. And by equating this representation of the change in price of the portfolio with the previous one, the one we just had before, we have this new formula in the bottom of this page here. This formula is completely deterministic. There are no stochastic terms. There's no Wiener process. And this is because we have done the choice of delta to be the first partial derivative of f with respect to x, which is the delta, in fact, of the option. Rearranging the terms of this last formula, we obtain this result, and this is clearly the Black-Scholes PDE, and as you can see, the magic has worked because it is deterministic. There is no randomness.